On the 26th of October, a high-risk Ukrainian air operation targeting a critical Russian supply hub culminated in the catastrophic failure of a multi-million-dollar defensive network. The mission, which was itself defined by a cascade of system malfunctions and significant pilot improvisation, began its high-risk ingress phase at approximately 2:40 p.m. local time. A lone Ukrainian Air Force MiG-29 crossed into Russian airspace, flying at treetop level, a profile designed specifically to stay below the detection threshold of long-range surveillance radars. The aircraft was armed with two French-provided AASM, or Armament Air Sol Modulaire, Hammer precision-guided bombs. Its objective was a border guard post at Bela-Berezovka, which Ukrainian intelligence identified as a vital logistics and ammunition node for Russian ground positions in Ukraine. The pilot faced immediate challenges. Russian electronic warfare systems jammed the aircraft's GPS, forcing him to rely on visual flight rules and a paper map. Compounding this, dwindling fuel levels meant the mission parameters allowed only one attempt on the target. At 2:41 p.m., the mission nearly failed. Flying at approximately 650 km per hour, the aircraft suffered a bird strike. A crow converging at 180 km per hour was ingested by the left engine intake, destroying the compressor blades spinning at 13,000 RPM and causing a catastrophic compressor stall. The severe asymmetric thrust caused the aircraft to lurch left, entering a rapid descent towards the forest. The pilot instinctively applied trained procedures: full right rudder to counter the yaw, pulling the control stick to arrest the descent, and activating the engine restart switch. The aircraft's altitude plummeted from 200 meters down to 160. The automated engine restart sequence required 30 seconds, but the pilot had less than 10 seconds before ground impact. Simultaneously, the event was briefly registered by Russian air defenses. At the Klomovo Air Base, an operator monitoring a Podlet K-1 low-altitude radar designed for targets like drones and missiles noted an intermittent contact. The operator had been tracking fleeting contacts for 2 minutes, likely the MiG-29 dipping between ridgelines and valleys. Just as the operator achieved a radar lock, the contact vanished again as the MiG-29 dropped altitude during the emergency. The lock lasted only 6 seconds, too short of a firing solution. The operator assessed the contact as an anomaly or ground clutter, dismissed as another flock of cranes, and hesitated to file a report, opting to take a scheduled break. This decision, based on an incomplete radar picture, proved critical. Minutes later, at a low altitude of 140 meters, the MiG's damaged left engine reignited. The pilot synchronized the turbines and stabilized the aircraft. The damage was severe. The left engine ran rough, with the compressor efficiency estimated at only 30%. The near crash consumed critical time and fuel, dwindling the pilot's reserve from 12 minutes to just 3. A new unmapped threat appeared: high-voltage transmission cables 60 meters above the valley. At 650 kilometers per hour, the pilot had 2 seconds to react, executing a 5G pull-up that cleared the top wire by less than 10 meters. The cable's electromagnetic field briefly disrupted the cockpit instruments. By the time the pilot pressed on, the Podlet K-1 radar station was in a shift change. The intermittent contact was logged but not actioned. The pilot reached his final checkpoint, a bend in the Desna River 10 kilometers from the release point. With one damaged engine and fuel for only one pass, he prepared for the attack. At 2:45 p.m., reaching the initial point 50 kilometers from the target, the pilot pushed both throttles to maximum and pulled the MiG-29 into a near-vertical climb. This high-risk pop-up maneuver is designed to toss the bombs on a high-arcing ballistic trajectory, allowing the aircraft to launch from outside the range of point defense systems. The physiological cost was immediate. The pilot endured 6 Gs, his G-suit inflating to squeeze his legs and abdomen. His vision grayed at 3,000 meters and narrowed to a tunnel at 5,000. By 6,500 meters, he was semi-conscious, his hand locked on the stick by muscle memory. Simultaneously, the damaged left engine vibrated violently, threatening to disintegrate. This maneuver, however, made the aircraft highly visible. The steep climb announced the MiG's presence to every air defense system within a 200-kilometer radius. As the pilot neared the release apex, the weapon's interface failed. The French AASM bombs were connected to the Soviet-era MiG via a non-standard interface, reported as a locally fabricated interface. Under 6 Gs at 7,000 meters, the system's voltage regulator failed. The weapons panel displayed liaison erreur, connection error, leaving the bombs deaf to the fire control computer. While the pilot, struggling with oxygen deprivation, cycled backup switches, a new threat emerged. 72 kilometers away, a Russian Su-35 fighter, vectored toward the earlier radar anomaly, acquired the climbing MiG. The Russian pilot locked the target and fired an R-37M, NATO AA-13 Axe-head, a long-range, hypersonic air-to-air missile. The MiG's radar warning receiver shrieked, "Missile launch bearing 045, closing at 2 kilometers per second." The missile would intercept in 36 seconds. The Ukrainian pilot could not yet evade. He still had to release his payload. Ignoring the failed digital interface, his right hand found the emergency pickle buttons, physical switches that bypass the fire control computer. At the 8,000-meter release point, he smashed the first button. After a 3-second delay, the first AASM bomb dropped and its rocket motor ignited. The second bomb released cleanly. Payload away, the pilot initiated a defensive maneuver. He rolled inverted and executed a 9G split S, an aggressive maneuver trading altitude for speed, pulling the aircraft back toward Earth. The pilot blacked out for 2 seconds from the G-force. When his vision returned, he was diving through 4,000 meters. The R-37M missile was still tracking. The pilot's countermeasures failed. The chaff dispenser fired 3 bundles and jammed, and the electronic countermeasures, ECM pod, overtaxed by the climb, had automatically shut down. With no decoys, the pilot executed a final defense, the notch maneuver. He turned the MiG-29 perpendicular to the missile's flight path, placing it on his 3 o'clock position. This reduced his relative velocity from the missile's perspective to 0. The R-37M's Doppler radar seeker, programmed to filter out stationary ground clutter, interpreted the target as an error and broke lock. The hypersonic missile passed 100 meters behind the MiG, its proximity fuse failing, and self-destructed. Warhead fragments peppered the fighter's tail, but the pilot was already diving back to treetop level. Meanwhile, the 2 AASM bombs, motors expended, reached an apex of 8,500 meters and began their 4-minute ballistic fall toward the Bela Berezovka post. They now faced their own layered defenses, compounded by internal malfunctions. Problem 1, propulsion failure. The first bomb's rocket motor ingested contaminated fuel, water vapor that had condensed and frozen at altitude, turning to steam in the combustion chamber. This resulted in the motor producing only 60% of its intended thrust. The bomb's processor calculated its trajectory would fall 2 kilometers short. Problem 2, electronic warfare. A Russian Kusuka-4 mobile EW vehicle near Bryansk activated, flooding GPS frequencies with 1,000 watts of jamming noise. Both bombs lost their satellite navigation links simultaneously and reverted to backup inertial navigation systems. However, INS is prone to drift, and the gyroscopes accumulated 2 meters of error every second, projecting a total miss distance of 480 meters. Problem 3, seeker interference. At 2:49 p.m., the second bomb's infrared seeker activated at 3,000 meters for terminal guidance. It immediately locked onto the sun, which sat directly in its path. The sensor was saturated by the 5,778 Kelvin heat source. The processor, recognizing a non-target, broke lock and searched again, finding only the solar glare. For 15 seconds, or 4 kilometers of flight, the bomb flew blind as its INS error grew. Problem 4, atmospheric interference. The first bomb flew into significant wind shear at 5,000 meters. An 80-knot gust from the jet stream's edge struck its control fins, yawing the weapon 20 degrees off course and tumbling its simple analog gyroscopes. The bomb entered an uncontrolled spin of 2 revolutions per minute, its fins at maximum deflection. its processor struggling to solve the differential equations needed to regain stable flight. Russian ground defenses attempted to intervene. An S-400, NATO SA-21 Growler battery at Klomovo detected the two small 0.2-meter RCS contacts. The operator, unsure of the profile but following standing orders, engaged, launching two 48N6 missiles. The engagement was futile. The S-400 is designed to intercept targets on predictable flight paths, not munitions in a high-angle ballistic freefall. The missile's computers failed to find an intercept solution and flew past harmlessly. At 2,000 meters altitude, the bomb's internal logic recovered. The first bomb's spin had carried it east, out of the sun's glare. Its IR seeker activated and immediately locked onto the heat signatures of three BTR-82A armored vehicles parked in formation with engines running. The second bomb, still blinded by the sun, initiated its backup guidance mode, contrast-based pattern matching. Ignoring heat, it searched for the building's distinctive geometric roof shape against the surrounding ground. This mode, developed from French experiences in Mali, achieved a successful pattern lock. Both bombs were now locked, diving vertically. The final layer of Russian defense, a Pantsir S-1, or a NATO SA-22 Greyhound point defense system, acquired them. At 8 seconds to impact, the Pantsir's radar locked the diving bombs. The attack profile was 87 degrees at 312 meters per second. The operator had not trained for this. The system's computer ran the calculation and displayed target outside engagement zone. The flaw was in the system's design for this scenario. The bombs, at 900 meters altitude, were already inside the minimum engagement range of the Pantsir's 57 E-6 missiles, 1,200 meters. The missiles require 1.5 seconds of flight to arm their fuses. The bombs would impact in 2.9 seconds. The operator fired 4 57 E-6 missiles anyway. They accelerated to Mach, but the physics was absolute. The missile's fuses armed at 400 meters altitude, just as the bombs passed below them. The missiles self-destructed, raining fragments on the compound. The operator defaulted to the Pantsir's twin 2 A38M 30mm autocannons. The guns, firing 2,500 rounds per minute, swiveled upward but hit their physical elevation limit at 85 degrees. The bombs were still at 87 degrees. The operator could only watch as thousands of tungsten core rounds passed fractionally behind the munitions. At 2:51 p.m., the first bomb impacted. Its damaged gyros resulted in a 12-meter offset, but it still punched through the building's roof at 312 meters per second. The 50-kilogram shaped charge detonated, but the asymmetric impact sent the superheated copper jet sideways, cutting through every load-bearing wall on the building's north side. The structure did not collapse, it toppled over. 17 seconds later, the second bomb, spiraling from its damaged fin, impacted 8 meters off target, striking the vehicle base corner. The 227-kilogram warhead and kinetic energy ruptured the fuel tanks of 3 adjacent BTR-82As. 1,500 liters of diesel fuel aerosolized, mixing with the air. The bomb's charge provided the ignition, resulting in a catastrophic fuel-air explosion that generated temperatures of 4,000 degrees Celsius, vaporizing the vehicles. The Ukrainian MiG-29, critically damaged and low on fuel, successfully egressed from Russian airspace and re-entered Ukrainian lines. The operation was a tactical success, neutralizing the Bela Berezovka border post and supply depot. It was not, however, a clean strike. The mission was defined by cascading system failures on both sides. The Ukrainian pilot succeeded by navigating a bird strike, engine failure, equipment malfunctions, and a hypersonic missile attack through skill and improvisation. Conversely, the Russian multi-layered air defense network, comprising the Podlet K-1 radar, the S-400 SAM, and the Pantsir S-1 system, failed completely. This was not due to a lack of technology, but because the attack profile, a combination of the pilot's emergency stall, environmental chance, and the high-risk ballistic toss, presented a scenario that the system's logic and their operators were not prepared to counter. The operation, though marked by extreme risk, achieved its primary objective.